Welcome, my friends! In this video, we will be calculating the least squares regression equation using the TI-84 calculator. I introduced scatterplots, correlation, and linear regression in a separate video, linked in the description, and I encourage you to watch that video first, especially if you are unfamiliar with the correlation coefficient R. As a brief review, a scatterplot graphs the relationship between two related variables, x, which we call the independent or explanatory variable, and y, the dependent or response variable. Our goal is to find the straight line that fits the dots the best. By best, we mean the line that has the smallest squared vertical distance from each point to the line. We call this line the least squares line, and linear regression helps us determine the equation of this line. The least squares regression equation has the form y hat equals a plus bx. Y hat is the predicted value for y based on the least squares equation. A is the y-intercept and is where the line will intersect the y-axis. B is the slope and represents how much y is predicted to increase for a 1-unit increase in x. X is the independent variable that will be used to predict y. The reason we have y hat instead of y is because the least squares regression equation is not perfect. We use the equation to predict y, and we call our prediction y hat, but our prediction will usually be a little bit off, which is why all of the dots on a scatterplot do not fall exactly on the least squares line. Now, there are formulas that can be used to find the equation of the least squares regression equation by hand, but they are a little bit complicated, and in this video, we will just be using the TI-84 calculator instead. If you want to know how to find the equation by hand using the formulas, see the video linked in the description. Listed are the age in years and weight in pounds of 8 males ranging anywhere from age 3 to age 18. The scatterplot of the data shows a strong positive correlation. As age increases, weight also tends to increase, and a straight line fits the data quite well. Our goal is to find the equation of the line that fits the dots the best. We would also like to find the correlation coefficient R to determine how strong the linear correlation is. Let's head to the TI-84 calculator to find these values. Now, in the calculator, there is a setting we will need to toggle to make sure that we get the correct output. You should only need to do this once per calculator. Press second, 0 for catalog, press the x to the -1 key to get to the d's, scroll down until you see diagnostic on. Press enter and then enter again. The calculator should say done. You should never need to do this step again. Now press Stat, Edit, and you will be at the stat lists. To clear out the lists, hover over the list you would like to clear, press Clear, and then the down arrow. Then enter all of the x values into L1 and all of the y values into L2. After you have entered all of the data in, press Stat again and arrow over to Calculate. Scroll down to option 8, which is lin reg a plus bx. You'll notice option 4 is also linear regression, but is in the form ax plus b. You will get the same answer using options 4 or 8, but option 8 matches the form of the equation we have been using, so that's the one that I will be using. Press enter, and you will be prompted to enter the x and y lists. If the lists already don't say L1 and L2, press second 1, enter, second 2 to change the lists. Leave the frequency list and store reg EQ blank, and press enter over calculate. You should now have A, B, R squared, and R. Looking at these numbers, we can construct the least squares regression equation. The equation is in the form A plus BX, as indicated by the calculator. Technically, the calculator should say y hat instead of y, to indicate that this equation makes predictions for y and won't find y exactly. So the least squares regression equation is y hat equals -7.18 plus 8.82x, if we round a and b to 2 decimal places. All I have done is taken the generic form of the equation, y hat equals a plus bx, and substituted in the value for a, -7.18, and b, 8.82. This is the equation of the line that best fits the points from the scatterplot that we looked at earlier. We also have the correlation coefficient R, which is 0.9814. Remember that r ranges from -1 to 1, and values close to 1, like 0.9814, represent a strong positive correlation, meaning as x increases, y tends to increase as well. A value of r near 1 or -1 also indicates that the points on a scatter plot will be very close to the least squares line. If you square this number, you get 0.9631, which is also given in the output. This is a number we call the coefficient of determination, and tells us that 96.31% of the variation in y is explained by x, or in this case, that 96.31% of the variation in weight can be explained by age. If you are ever asked to interpret r squared in the context of a regression problem, this is how you should word your response. Recall that the equation of the least squares line is y hat equals a plus bx. Our equation is y hat equals -7.18 plus 8.82x, as determined in the previous slide. Now there are two main things that this equation is used for. One is to interpret the slope. In general, the interpretation of the slope can be worded as, for a 1 unit increase in x, y is predicted to increase by b, where b is the slope. For this problem, x is age and y is weight in pounds. So the interpretation of the slope is that for a 1 year increase in age, the weight of a male child is predicted to increase by 8.82 pounds. If you are ever asked to interpret the slope of a linear equation in the context of a problem, this is how you should word your response. The other main use of this equation is to make predictions for y using values of x. For our example, the initial dataset did not contain any male children aged 12. So we might plug in x equals 12 into the equation in order to predict the 12-year-old's weight. We have y hat equals -7.18 plus 8.82 times 12, which simplifies to 98.66. We predict that a 12-year-old male will weigh about 99 pounds. Let's try another one. What if we have a male that is 38 years old? How heavy would our model predict this individual to be? Well, we have y hat equals -7.18 plus 8.82 times 38, which simplifies to 327.98. We predict that a 38-year-old male will weigh about 328 pounds. Something doesn't seem right here. I wonder if you can put your finger on it. Most 38-year-olds are not 328 pounds. Remember that our dataset was made up of children from the age of 3 to 18. We are now using the model to try to predict the weight of someone aged 38, way outside of the range of ages used to build the model. In general, when we try to make predictions for y using values of x that are not within the range of the initial dataset, we call that extrapolation. This is like when we used x equals a 38-year-old to try to predict the weight in our equation. The predictions made using extrapolation should be evaluated with caution, as they will often be inaccurate. On the other hand, when we try to make predictions for y using values of x that are contained in our initial dataset, such as when we predicted the weight of a 12-year-old earlier, we call this interpolation. The predictions made using interpolation will generally be more accurate than those made using extrapolation, especially if the correlation is strong. Okay, the final thing I want to do is graph the least squares line onto a scatter plot. As you may already know, in order to draw a straight line, you must have 2 points. The 2 points we need are 0, a and x bar, y bar. It turns out that these 2 points will be on every single least squares regression line. Once you have found the regression equation, you will know the point 0, a, as a is just the y-intercept or constant in the least squares regression equation. In our case, 0, a is just 0, -7.18. If this point doesn't fall nicely onto the scatter plot, you can pick any other value for x, plug it into the equation, and find a point on the line. For example, 12, 98.66 is also a point on the line that could be used, which we predicted earlier. X bar, y bar is easy to find if you have already ran linear regression on the TI-84 calculator. Assuming you have the data in lists 1 and 2, press stat, arrow over to calculate, and run 2 variable statistics. Make sure you have L1 as the X list and L2 as the Y list, and that the frequency list is blank. Press calculate, And you should have x bar, the mean of your x variable, which we see here is 10. And if you scroll down, you should see that y bar, the mean of your y variable, is 81. So the second point, x bar y bar, is 10, 81. Now all you have to do is plot the 2 points and connect the dots. We have 0, negative 7.18 and 10, 81. Connect the dots to draw your line, and ta-da! You have drawn the least squares regression line. Alright, my friends, that wraps up our discussion of linear regression. We will be exploring many more fun and exciting statistical topics that you won't want to miss, so make sure to check out our other videos.